Given this graph, fx equals 2 sine 2x minus pi over 4 plus 3, you want to graph it, labeling the axes and extrema. Then find a trigonometric function with the same numbers as the above graphs that has asymptotes at the extrema of this graph and analyze it completely. First, remember our graph? It's this. We use the dilation, reflection, translation rule. First is dilation. We stretch it to be twice as tall. And then, because of the 2 in the middle, we cut the period in half, so now it's pi. Because we have no reflection, that's fine. Then, next is translation. You move it to the right, pi over 8. This says 2x minus pi to the 4, but that's because if you factor this out, it turns into an 8, because 2 times pi over 8 is equal to pi over 4. Then you move it up 3. Your graph should now look like this. Now to find the graph with asymptotes of the extrema. First, we got to find out which function we're going to use. When sine is 1 or negative 1, cosine is 0, because sine 90 equals 1, while cosine 90 equals 0. Sine 270 equals negative 1, cosine 270 equals 0. 1 and negative 1 are extrema of the sine graph. So secant will have asymptotes at the extrema, because at the extrema, cosine is 0, and 1 over 0 is not defined. Keep everything except the functions, and then you'll have this graph. Note the asymptotes where the extrema are. Blue one is a sine. I kept it so I could show you, and the red one's a graph of interest. So, now it's time to analyze the graph. Whenever I say k, as you see here, and here, and here, it can only be an integer. First, domain. Secant has a value for every x except the extrema of sine, because then it's an asymptote. We already mentioned the extrema of sine above. It would normally be 2 pi over 2 plus 2k pi, but they get shifted just like the graph in DRT. First, we cut everything in half because of the 2 in the parentheses. This parentheses. So now we have this. Reflection, you don't do anything. There were no reflections in the original graph. You shift over pi over 8 just like you did with the other graph, and you have this. This is where secant does not have a value. So the domain is any value where x is not this. Range. Secant can be any value between infinity to negative 1 and 1 to infinity. The same hold true despite any horizontal dilation. Let's just call y equals secant x and see what we can reach with our dilations. 2y equals negative 3. We can't get smaller than 1, so 5 appears to be a lower cap for when secant is positive. It also can't get any larger than negative 1 and still be negative, so 1's kind of an upper cap for when secant is negative. So the range is therefore this. Ooh, there's the parentheses there. It first starts increasing after reaching its lower cap when positive, and then stops increasing when it reaches its upper cap when negative. When you look, lower cap when positive, upper cap when negative. It reaches the low, and there is an interruption in between, the asymptote. It reaches the lower cap at x equals pi over 8, and then the upper cap reaches pi over 8, and the asymptote is here. So, and this repeats every period, which we established before was pi. So this is the interval. Everything's a parentheses, because at pi over 8, it's not doing anything. Well, it's not increasing or decreasing is what I mean to say. So it can't be increasing. Decreasing. Back to the graph. Starts decreasing after hitting upper cap when negative, and decreasing until it hits the lower cap when it's positive, with a gap at the asymptote. It reaches the upper cap at this value, and the lower cap gets hit at this value, and there's an interruption here because it's another asymptote. This also repeats every period or every pi. X-intercept. Let's plug in 0 for y in the function. After doing your algebraic gymnastics, first, before I continue to here, note that arc cosine negative 2/3 is 2.300 rad, but another value that leads to value cosine is 2 pi minus 2.30, also rad as well, because cosine's graph is symmetrical about x equals pi. So some more algebraic gymnastics, and you get two solutions for where x is. This repeats every x, and the two x-intercepts are these values, which makes sense. If we look at the graph, every period there's two x-intercepts. Negative. Before we go on to the y-intercept, we can talk, now that we know it's x-intercepts, we can talk about when it's negative and positive. It's negative in the negative half of the secant graph, except for the area between the two x-intercepts and at the two x-intercepts themselves. 0 is neither negative or positive, so you cannot count it. The negative half spans from 3 pi over 8 to 7 pi over 8 in the period in which these particular x-intercepts are concerned, and this repeats every pi, just like the graph. Therefore, these are the intervals. Positive. The entire positive half is not affected by the x-intercepts. That's negative pi over 8 to 3 pi over 8. The entire positive half, this is pi over 8, this is 3 pi over 8. Also, the area between the two x-intercepts are positive too, and this repeats every pi. This is the positive half. This is x-intercept. And this is the other x-intercept when it starts turning negative again. This is where it first starts being positive, and that's where it stops being positive. Y-intercept, plug in 0 for x. And now instead of putting 0 here, we put 0 here. And secant of negative pi over 4 is root 2. So now we have our y-intercept. Because there's a 2 within the parentheses, the period, as we had to establish to find all of those, is pi. Secant doesn't have an amplitude. That's really only for fluctuating functions like sine and cosine. Secant doesn't have a maximum or minimum. It can reach both negative and positive infinity without an issue. It can get infinitely large and infinitely small. Secant doesn't converge to a value. End behavior is kind of a moot point because it has an incessantly repeating period. If you notice, it repeats every period. It can't reaching negative infinity. It keeps looping, and it won't ever reach one set value. It does not converge, so it doesn't have an end behavior.